Hello everyone, this is Kamrul Hasan, a PhD student from Rochester Institute of Technology. I would like to talk on a very memory efficient architecture for segmentation and clinical parameter estimation from cardiac Cine MRI. So if a patient who is suspect of having a cardiomyopathy is taken to the hospital, and in some cases different series of cardiac MRI will be taken to augment the diagnosis. Among different cardiac MRI, Cine MRI is considered as a gold standard thanks to its high spatial and temporal resolution. However, to assess the cardiac functions such as ejection fraction and myocardial mass, we need the segmentation. Also, to create anatomical heart models for surgical planning, we need automatic segmentation of cardiac structures. There are several existing segmentation approaches which are broadly classified into three categories, such as weak prior-based and a strong prior-based approach. Nevertheless, they have disadvantages. So deep learning-based approach is getting very popular recently. And two of the authors use DenseNet and fully convolutional networks for LV, RV, and myocardium segmentation. However, none of the research work focused on network optimization. So that is the motivation of our research. From a machine learning perspective, image segmentation is a multi-class classification problem with the goal to assign each voxel a target label. In this example, we feed a two-dimensional cardiac MRI into a ROI detection block that will detect the region of interest, which is fed to the convolutional neural network, which will output a so-called probability map of each of the tissue and also the background class. And we combine those maps into an automatic mask by assigning the class with the highest probability to each of the voxel. Our second objective is to analyze the cardiac functions from the segmented cardiac architecture, and most importantly, to reduce model parameters for network optimization. Although the integration of regularization techniques has been a very growing trend nowadays to improve the generalization performance such as dropout. But this is not a desired way to prune some of the weights because it does so very randomly. So the motivation of this research is to use the concept of group convolution where filters are split into several groups and each of the groups are connected to a subset of the previous layer's feature maps. As a result, the computational cost is divided by the number of the groups. However, in a group convolution, those filters are predefined, so we want to make it more dynamic. So our proposed method is to use those group convolution but make it learnable, where the redundant connections are pruned out through multi-stage process, and which consist of condensation stages, which will be used for pruning out those redundant information, and in the optimization stages where training will be performed. To start this process, we had to select some of the predefined parameters such as condensation factor and also the number of the epochs. And when we are done with those selections, we calculate individual filter weights for each of the connections for each of the group, and then put those weights in a matrix of each column for each of the groups. And when we are done, then we first sort out those filters and compare each of the filters with the average value. If each of the individual filter weights is really very less than the average one, we put a zero mask in that matrix. And in that way, we can remove those redundant informations or redundant connections and make the network very light. This is our proposed LCONET model that consists of two blocks. One is the ROI detection block, and second is the heart segmentation block. And the heart segmentation block consists of depth-wise separable convolution, and also the DenseNet architecture is replaced with the CondensNet block, where each of the CondensNet learned group convolution is used in the 1-by-1 convolution with some permutation in between 1-by-1 and 3-by-3 convolution. To reduce the computational complexity, we used Fourier transform-based approach for ROI detection. Fourier transform was used to determine the fundamental H1 component. A 2D inverse FFT was then used to transform back into the original spatial domain. After that, we applied a canny edge detection to find the center of the LV using circular half transform. The maximum across the LV likelihood was then selected as the center of the ROI, and the square patch of fixed size was cropped. For the dataset, we used Mikai Stackham 2017's challenge dataset that has the short axis slices of the 100 patients for both LV, RV, and the LV myocardium. We also used different data augmentation techniques during training. So for the loss function, we used the dual loss. One is the cross entropy loss, and another is the dice loss. So the dice loss is almost similar to find out the dice similarity coefficient. Just we replaced the target level with the posterior probability, and then we calculated for multi-class. And cross entropy loss is nothing but the negative log likelihood, but we used the weighted cross entropy loss, where we multiplied the log likelihood with the true weight, and which was calculated from the true label and contour. For the evaluation of segmentation, we used the DICE score, and for the evaluation of clinical parameters, we used correlation coefficient. These are some of the tuned hyperparameters. The overall dataset was divided into 70% training, 15% validation, and 15% testing. This table shows the LV blood pool segmentation results in terms of both DICE scores and Hausdorff distance, and our proposed ELCONET model achieved best results compared to the 5 other state-of-the-art model. This is also true for LV myocardium segmentation results in terms of DICE scores and LV, although our proposed model couldn't achieve best results for RV blood pool segmentation. However, it achieved comparable results for both end-diastole and end-systolic phases, and even better Hausdorff distance. This table shows the clinical parameter estimation in terms of the correlation coefficient for 5 different cardiac parameters, and our proposed model achieved best values in comparison. This is a graphical comparison between clinical parameters estimated using our proposed model and the ground truth for both healthy volunteers and the cardiac patients, which shows very minimal gap from the ground truth except for the RV volumes. Our proposed model runs on the ACDC dataset using 50% of the memory requirement of DenseNet and 60-fold reduction in memory from the MUNet architecture. This is the qualitative results that shows the segmentation mask from apical slice to the basal slice for both end-diastolic phase and end-systolic phase. For better visualization of qualitative results, we computed the surface distance from ground truth mask to automatically segmented 3D model. This color bar shows the surface distance, more the red, more the distance gap, and vice versa. As you can see from the video, the left one is for the LV model, which has a very tiny spot of surface distance from the ground truth. The middle one is for the LV myocardium, and we can see a small spot at the very bottom part, which shows the surface distance from the ground truth. And the right one is for the RV model, and which has a larger distance of surface distance, so it shows more red on the very top. So to the best of our knowledge, this is the first work to efficiently use of wet pruning methods for segmentation and quantification of cardiac structures that leads to high computational savings without compromising the accuracy. And our proposed model achieves best results in terms of Hausdorff distance, DICE scores, and also the clinical parameters, and showed at least 3.7% improvement over the current methods, and also a very less memory requirement compared to the DenseNet and other unit type architectures. For the better segmentation results of the RV, we will explore the more slice refinement and slice misalignment correction as a future work. I would like to thank all of our collaborators, my advisors, and my group members. Thank you all.